How would you describe the trip from your home to your school before COVID? You probably include whether you walk or rode a bus, how far away the school was, and how long did it took to get there. Scientists talk about motion in a similar but very specific way. Hi, and welcome back. In today's science episode, I will talk about motion.
Motion and position. You do not always need to see something move to know that motion has taken place. For example, suppose you look out a window and see a mail truck stop next to a mailbox as shown in figure 1. 1 minute later, you look out again and see the same truck stop farther down the street. Although you did not see the truck move, you know it moved because its position relative to the mailbox changed. Reference points. A reference point is needed to determine the position of an object. In figure 1, the reference point might be a mailbox. Motion is a change in an object's position relative to a reference point. How you describe an object's motion depends on the reference point that is chosen. For example, the description of the mail truck's motion in figure 1 will be different if the reference point were a tree instead of a mailbox. After a reference point is chosen, a frame of reference can be created. A frame of reference is a coordinate system in which the position of the object is measured. The x-axis and y-axis of the reference frame are drawn so that they are perpendicular to each other and intersect the reference point. Coordinate systems. Figure 2 shows a map of the city where the mail truck is delivering mail with a coordinate system drawn on it. The x-axis is in the east-west direction, and the y-axis is in the north-south direction, and each division represents a city block. The post office is located at the origin. The mail truck is located 3 blocks east and 2 blocks north of the post office. Change in position. Have you ever run a 50-meter dash? Describing how far and in what direction you move was an important part of describing your motion. Distance in a 50-meter dash, each runner travels a total distance of 50 meters. The SI unit of distance is the meter. Longer distances are measured in kilometers. 1 kilometer is equal to 1,000 meters. Shorter distances are measured in centimeters or millimeters. 1 meter is equal to 100 centimeters and to 1,000 millimeters. Displacement. Suppose a runner jogs to the 50-meter mark and then turns around and runs back to the 20 meters mark as shown in figure 3. The runner travels 50 meters in the original direction, east. So this is the first, right? Here, 50 meters. And then 30 meters in the opposite direction, west. So the total distance that she ran is 80 meters. How far is she from the starting line? The answer is 20 meters. Sometimes you may want to know the change in an object's position relative to the starting point. An object's displacement is the distance and direction of the object's change in position. In figure 3, the runner's displacement is 20 meters east. The length of the runner's displacement and the total distance traveled would be the same if the runner's motion were in a single direction. For example, if the runner ran east from the starting line to the finish line without changing direction, then the distance traveled would be 50 meters, and the displacement will be 50 meters east. Adding displacement. You know that you can add distances together to get the total distance. For example, 2 meters plus 3 meters equal 5 meters. But how will you add displacement 50 meters east and 10 meters east? Directions in math problems are much like units. You can add numbers with like directions. For example, suppose a student walks 5 meters east, stops at a crosswalk, and then walks another 5 meters east, as shown on the left in figure 4. His displacement is 5 meters east plus 5 meters east equal 10 meters east. But what if the directions are not the same? Then compare the two directions. If the directions are exactly opposite, the distance can be subtracted. Suppose a student walks 10 meters east, turns around and walks 5 meters west as shown in the center of figure 4. The size of the displacement will be 10 meters minus 5 meters equal 5 meters. The direction of the total displacement is always the direction of the larger displacement. In this case, the larger displacement is east, so the total displacement is 5 meters east. Now suppose the two displacements are not in the same direction or in opposite direction, as illustrated on the right of figure 4. Here the student walks 4 meters east and then 3 meters north. The student walks a total distance of 7 meters, but the displacement is 5 meters. In the roughly northeast direction, 4 meters east and 3 meters north cannot be directly added or subtracted, and they should be discussed separately. The rules for adding displacement are summarized in Table 1. Number 1. Add displacements in the same direction. Number 2. Subtract displacement in opposite directions. Number 3. Displacements that are not in the same or in opposite directions cannot be directly added together. Now, let's talk about speed. Speed. Think back to the mail truck moving down the street. You could describe the movement by the distance traveled or by the displacement. You might also want to describe how fast the truck is moving. To do this, you need to know how far it travels in a given amount of time. To describe how fast an object moves, scientists use the object speed. Speed is the distance an object travels per unit of time. Calculating speed. Any change over time is called rate. For example, you could describe how quickly water is leaking from a tank by stating how many liters are lost each hour. This will be the rate of water leakage. If you think of distance as a change in position, then speed is the rate of change in position. Speed can be calculated from this equation. Speed in meters or seconds, speed is meter times seconds, equal distance in meters divided by time in seconds. In SI units, distance is measured in meters and time is measured in seconds. Therefore, the SI unit for speed is meters per second. Sometimes it is more convenient to express speed in other units, such as kilometers per hour. Table 2 shows the speed of some common objects. For example, if I'm talking of an Olympic 100-meter dash, I will use meter per second. A car on a city street, I will use meters per second. A car on interstate highway, meter per second. Commercial airplane, meters per second. And here are the speed of it. Example problem 1. Calculate speed. A car traveling at a constant speed covers a distance of 750 meters in 25 seconds. What is the car's speed? What do we need to identify? The speed. What do you know from the problem? The distance, that is 750 meters, and the time, 25 seconds. So now you use the formula. My answer is 30 meters per second is approximately the speed limit on a US interstate highway, so the answer is reasonable. Constant speed. Suppose you are in a car traveling on a nearly empty freeway. You look at the speedometer and see that the car's speed hardly changes. If the car neither slows down nor speeds up, the car is traveling at a constant speed. If you're traveling at a constant speed, you can calculate your speed by dividing any distance interval over the time it took you to travel that distance. The speed you calculate will be the same regardless of the interval you choose. Changing speed. Usually speed is not constant. Think about riding a bicycle for a distance of 5 kilometers. The bicycle's speed will vary as it shows in figure 5. As you start out, your speed increases from 0 kilometers per hour to 20 kilometers per hour. You slow down to 10 kilometers per hour as you pedal up a steep hill and speed up to 30 kilometers per hour going down the other side of the hill. You stop for a red light, speed up again, and move at a constant speed for a while. Finally, you slow down and come to a stop. Checking your watch, you find that the trip took 15 minutes. How would you express your speed on such a trip? Will you use your fastest speed, your slowest speed, or some speed between the two? Two common ways of expressing a change in speed are average speed and instantaneous speed. Average speed. Average speed is one way to describe the speed of the bicycle trip. Average speed is the total distance traveled divided by the total time of travel. It can be calculated using the relationship between speed, distance, and time. For the bicycle trip just described, the total distance traveled was 5 kilometers, and the total time was 1/4 hour or 0.25 hours. Therefore, the average speed was 20 kilometers per hour. Instantaneous speed. Suppose you watch a car's speedometer like the one in figure 6 go from 0 kilometers to 80 kilometers per hour. A speedometer shows how fast a car is going at one point in time or at one instance. The speed shown on a speedometer is the instantaneous speed. Instantaneous speed is the speed at a given point in time. When something is speeding up or slowing down, its instantaneous speed is changing. The speed is different at every point in time. If an object is moving with constant speed, the instantaneous speed does not change. The speed is the same at every point in time.
I hope you found this video interesting. Thanks for watching and until the next one. Bye!